sense. So this data loses its whole knowledge what it has once we randomize it and do not have a time inference and the sequence what we see here. So this is a key characteristic of time series data. To understand a time series data better, let us look at a non-time series data. So here what you see height and weight of students in a class, and if you look at these numbers, uh, uh, so there is no particular order. So if I randomize this data, shuffle it, and even give to somebody, the same inferences will be drawn from the particular data. So here what we see that order is not that important. The sequence is not that important. But when we talk about time series data, sequence is very important. So the data order is the key difference in time series data and non-time series data. So next, let us see what are some examples of time series data and in real life. And first thing comes into industrial process data. So as we know, the industrial process keep running over time, and all these sensors like flow sensor or temperature sensor, they keep logging the information data against those time stamps, as we have seen an example in previous slide. So all of these qualifies as a time series data. Next is once we look at the financial data, for example, stock prices. So we see stock prices moving day by day, or even hour by hour, or second by second also. So there is a time dependencies on stock prices. Similarly, we see currency exchange rates, interest rates from financial data, and they have a very similar time dependence and time sequence. If you look at the retail data, so goods prices. So goods prices keep changing day to day, and it forms a nice time series. So similar thing happens with sales volume, interest rate, or how many new customers are coming to a particular business. So all this data is a typical example of time series data. So apart from these, there are a lot more other data which makes time series data. For example, if you look at the weather data, temperature data. So we have temperature data every hour that is logged against time, and it changes sequentially. So that qualifies for the time series data. We keep hearing every day about COVID-19 infections daily count, and that forms a time series data. So any data which has a time and sequence into it qualifies for a time series data. So if you look at all these data together and try to see that where is majority of time series data lies, and that is into the manufacturing industries, because almost more than 95% data which is being generated by manufacturing industries and being stored is time series data. So now we have a basic understanding of time series data. Let's get into time series analysis. And time series analysis is nothing but understanding the data a bit better. So how we can decipher it, how we can understand a particular data set with respect to all its component. So there are some component of time series data, and it is divided into two components: systematic components and non-systematic components. So let us first look into systematic components. What is there in systematic components? So once we take a time series data, the first thing what we look into is a level of data, and level of data is nothing but this average value of data. So it's pretty evident where the average lies in the particular data set. So that is called level. Second thing is about the trend in the data. So some of the data you might see that it is rising. So here we can see there is a trend. This data is going high month by month. So there is a trend in data. And trend trend could be, there will be multiple trend in one data set. So for example, if you look at this particular zone here, you see that the values are dropping, then values are again rising. So this is a local trend what we are able to see. But there is also a long range trend and long-term trend, which we can see that this particular time series has an increasing trend overall on long-term basis. So this is called trend into data. And then third part comes is the seasonality. So seasonality is basically the cycles. So when there is a certain repetition or pattern in the data, we call it seasonality. So this data is a daily temperature data being recorded over years. And as you can see that this being high at summer, then it reduces into the winter, again it goes high into summer. So every year this particular pattern is being repeated, and this is called seasonality. And again, like trend, there could be a different frequency of seasonality. So what we are seeing currently in this particular chart is a seasonality which is changing over years, and that is seasonal variations. But if we zoom it and look at the day level, then we'll find another pattern repeating itself every day. For example, morning temperature is low, afternoon it increases, evening again it start decreasing, and this is being followed every day. So that is a different frequency, but that is another seasonality present into the data. So data could have a different seasonality within one data set itself. So again, these three are called systematic components, and we call it systematic components because we can understand it, we can predict it, we can decipher it. So that's why we call it systematic component. And what is non-systematic component in data is a noise. So every data has certain amount of noise, and we cannot explain it, and we cannot predict it into the data. So that's why we call it as a non-systematic components. So previous slide, we understand about systematic and non-systematic component, and we also talked about that systematic components can be understood, it can be deciphered, it can be taken out from the data. So here we'll understand how that works, how we can take out all these different components from the data. So what you see here, this is airline passengers over time data from 1949 to 1960. And this is a raw observation, and very clearly what you can see here that there is a trend. So it is increasing over time, there is a trend, and also there is seasonality. So I see that a particular time, maybe some vacation time in a year, there's more travelers, and then again it drops. So that is being observed. So those seasonality is also present in this data. So now let us understand, if we try to split it into different components, what we talked at previous slide, how it looks like. So once you decompose it and try to look at trends, so it's very clear. So here is the trend. So this whole flying passengers are increasing over time. That's we see. So this is trend. Next, what we see is seasonality. So once we break this data for seasonality, then seasonality components is taken separately, and we can see that how it is changing. So every year it goes high, comes down, again goes high. So those patterns are being repeated. And then once we remove trend and seasonality from the actual data from here, then finally we get a noise plus signal. So as I explained that noise is a non-systematic components which cannot be understand and cannot be modeled, but it comes along with the signal even if we remove these all systematic components out of it. But there are techniques to do noise reduction or noise elimination. So those are signal processing techniques which can be applied further to this remaining noise plus signal data. remove noise from it, and only getting signal which can be given to machine learning models or classical statistical models to learn about. But we are not going to cover that in this session. So what are the tools we have readily available which can do this kind of decomposition? And good news that we already have a Python library called stat models. So once if we supply this kind of actual data, this particular library function, then it will split into these three components and give it to us. So we can very clearly understand the trend, seasonality, and actual signal out of time series data what we get. And the similar there's another option in our programming language. This particular library TTR can be used for similar applications. So now there is a very important concept in time series, and that is called stationarity of data. So let us understand what it is. So there is two classification of time series data: stationary time series and non-stationary time series. So let us understand what is a stationary time series data. So as you can see, this particular data set, it is called as a stationary time series data. So what are the characteristic of this particular data? Once we see that there is no trend or there is no seasonal effect. So that's what we are able to see here. So that qualifies one characteristic for the stationary time series. Also, another qualification criteria is statistical parameters like mean, variance, etc., consistent over time. So what does it mean that if you take a period, for example, let's take a first half of the year from January to June, and we calculate a mean of this data, standard deviation of this data, and then take another period which is from June to December, second half of the year, and we calculate again the mean standard deviation. So what we find that these two things are not very different from each other. They are very close by. So if time series data qualify these criteria, there is no trend, there is no seasonality, and it does not change much over time in terms of statistical parameters, mean and variance, then it qualifies for a stationary time series. So what is non-stationary time series? So it's very obvious. Whatever is not a stationary is a non-stationary. So here we see this data set, which we have seen previously also, passengers over years 1949 to 1960. And see, we can see here we have trend, we have a seasonal effect as well. And if you take mean and variance at different part of this data, they are going to be different because there is a trend. Data is changing over time. So so these are definitions and basic characteristic to understand a stationary and non-stationary time series. But question is that why should we are learning about it? Why should we bother about it? And the answer is the non-stationary time series data is difficult to model, and it hampers all the modeling and learning process of the statistical models as well as some machine learning models. And second reason that is that there are different kind of models available where we can feed stationary time series data. So those are suitable for modeling stationary time series data. And if it is non-stationary, then we have to use different kind of models, different kind of methods to make forecasts or for the particular time series. So that's why understanding about stationarity of data is very important. So we talked about stationarity, and also we learned that that is not very good thing when we go for the modeling. It hampers the modeling accuracy, model results, and accuracy of the models. So how to remove it? And so suppose we have a non-stationary data, how we can make it stationary such that we can feed to some models to have a better result. And a very one way of doing is differencing the data. So here you see that this is a data which has a trend. So we want to detrend it, and that is one of the component which is making it non-stationary. So if you want to detrend it, the very simple technique works very well, that you difference it. So you take a current value and then subtract it from the previous value, and that corresponding outcome will provide us a stationary, not a stationary but detrended series here. So to just explain with this particular data, say we have a monthly data, and we have a data from January, and we subtract it from the December data, and we keep doing that. We subtract February data from January data, and that subtraction will create a new series, and that will look like something like this. So we see that this data does not have trend. So what we have done, we have taken a data which had trend, and then we detrended it. We made it without trend. So this is the way to remove trend from the data. And suppose data also have seasonality, and as per our definition, uh, both trend and seasonality has to be removed from the data to make it stationary. So how should we remove the seasonality from the time series data? And technique here again is a differencing. Uh, but So for example, this particular data set is a daily temperature data, and that's why we are seeing this seasonal cycles, seasonal ups and downs, which is repeating again and again every year. And if you want to remove seasonality from it, we can difference it same day previous year. So for example, if we look data on 1994th of August, we difference it from 1989 data 4th of August. So if we do that, then we'll be able to remove all these cycles completely from the data. And by doing that, we'll get something like this. So here you see that all these cycles has been removed, and data is free from seasonality. So these are some very simple techniques to detrend data and remove seasonality to make non-stationary data stationary and make it suitable for the modeling purposes. Okay, so so far what we have learned about time series. What is time series data? We learned about how time series analysis, how to understand our data. We understand about systematic, non-systematic component. We can break down the systematic components, trends, seasonality, etc., and also stationarity and stationary data concepts we have understood so far. So let us move into next phase and here the time series forecasting. So now we have a time series, and we want to make a future forecast out of it. So first we'll go over classical statistical approaches and see that how those can be applied to make a time series forecasting. So first kind of models comes here is called autoregressive models, and as a short form, it is also says AR models. So suppose we take an example of same daily minimum temperature data, what we have seen in previous phase, and we look into this data. And if there is a relation between past data with future data, if that exists in the particular data set, that is called that data is auto correlated. So the past value has a relation with our future values, and if data has auto correlation, then we can apply these kind of autoregressive AR models. So now, if you look at this daily minimum temperature data and try to understand whether there is a relation between previous data set with a future data set. So here, if we do a simple exercise and we try to plot the current value with a one step future value. So for example, we say we take one data set, one data point of 1st January, and that is on x-axis, and then we have data from 2nd January, and that is going to on the y-axis, right? So if we and we repeat it again, we take 2nd January data on x-axis and 3rd January data on the y-axis. So basically, we are plotting a past value against one step future value. And what we see if we do these plots from this data set, we see this kind of behavior, this kind of data, what we see. What it indicates that there is a relation. So you see that this is very nicely looks like it's kind of linear. We can have approximate linear line through it. So there is a autocorrelation in this particular data, and we can apply autoregressive kind of models here. So once we know that future value is related with the past value, then we can use past value or current value to predict the future value. So that's the whole concept behind autoregressive models. So for example, in this particular case, if you look at, we saw that this is kind of linear relation with future value with the current value basis on this data when we plotted here. So we can make a very much linear model, and here is a linear model. What we see, y is equal to mx plus c, ma plus b. So here, so this is the model which can be fitted to it on the basis of it, and it could predict the future value if we know the current value. Okay, so another type of models are moving average models, and as we looked at previous autoregressive model, and we come up with a model which made a forecast like this. So you see the red line here is a forecast, and the blue line is the actual. And you know, any model you will make, it is not going to be perfect, so it will not be point to point. So there will be always be some errors, and so there is an imperfection in all the models, and this imperfection once present into the models, so we can calculate the error into their predictions. So for example, suppose today we make a forecast for tomorrow, and once tomorrow comes and actual values are available, then we can calculate this error, that what was forecasted and what was actual. And this error is going to have a pattern for these imperfect models. So once in these kind of moving average models, we manipulate these errors and then try to predict future errors. So once we know the future errors, we can further improve the accuracy of overall models what we have built in previous stage. So this is a method which is called moving average models. So now we'll take a very high-level overview of popular statistical model for time series forecasting. So we looked into AR model, autoregressive model. We looked into the moving average models. And now, if we combine these two together, autoregressive AR and MA for moving average, so that gives us ARMA model. So here we are taking advantage of dependence of relation between the past value and future value using the autoregressive, and then we are further improving that model by applying the error model using moving average. And this must be used when data is stationary. So if data is non-stationary, then you have to apply the techniques we have learned to make it stationary, and then feed it to ARMA model. And then here a further extension of this ARMA model, and there is additional I that is stand for integrated. So ARMA, this is called ARIMA model, and ARIMA model is a extension of ARMA model with differencing. And as we saw that we use differencing for detrending the data, so removing trend from the data. So suppose we have a non-stationary data which have only trend but no seasonality. So this model will be a better option for that particular data. Then there's a further extension of ARIMA, that is S-ARIMA model, and here S stand for seasonality. So it also handles seasonality within the model itself. So it can be used for a complete non-stationary time series data. So you can directly apply S-ARIMA and when data is non-stationary. There are other models are also available, Arimax, Arimax. So these models allows us to take some additional parameters other than the one we are trying to forecast. So those inputs also can be provided in these models and to have a better forecast results. So what is pros and cons of these classical models? And if you look at the pros, these are simple models. Computationally not that expensive, and it deals with the temporal structure very efficiently. And as I told, it's computationally not much expensive and explainable. So we can break it out and we can explain the results much better manner. And there are inbuilt libraries in Python and R which can be utilized. So what are the cons of these classical models, what we have discussed? And the one major one is it does not work very well with the noisy data. So if there is a noisy data that needs to be denoised before feeding to these models. And if there is a stochastic trend, so stochastic trends mean that it's not clear upgoing or downward trend, but it is going up and down and not very one way. So those kind of trend and seasonality, also multiple seasonality in the data makes forecast difficult, and model accuracy suffers in this case. And most of these models assumes linearity. So if behavior is non-linear, these models difficulty modeling it. And again, multivariate dependence is hard to model. So that is another problem with these classical methods. So now next comes time series forecasting using machine learning or deep learning approaches. So let us look into this. So how we can use supervised ML for time series forecasting? So I'll take very simple example to explain it, that how it can be utilized. Here, suppose we have a historical data, and it's very simple data that time stamp T1, T2 to T6, T5. We have data 2, 3, 4, 5, 6. So you see that this is sequence what we have, and this is time stamp what we have. And what we want is to predict that what will be value at T6. So that is the forecast. So now we have to do some feature engineering for feeding this to ML models to learn. And feature engineering would be like we have to prepare an input and then output. So we can say that this is current value is 3, and then future value is going to 4, and then we can take some previous value. You can choose to take previous value if there is we are feeling that there is a dependence, there is a sequence. So we are going to take a value at t-1 as well. So in this way, we see 2, 3, and then future value is 4. So if current value is 4, then previous value is 3. So 3, 4 makes as the input, and then 5 is output. Similarly, if 5 is my current value, then I'll also take my previous value as one of the feature into model, and then 4, 5 goes into model, and then the output is going to be 6. So this is X for the machine learning model, and this is Y for the machine learning model. Now we train this model, and we have a trained model available with us. So what input we'll give, if you want to predict what is going to be value at T6, so we are going to provide 2 inputs. As we see here, X has 2 inputs in every row, and that is current value, and current value here T5 is 6, and then just before value of the current value, that is T4, which is 5. So once we give T4 equal to 5 and T5 equal to 6, the trained model has learned those patterns, and on the basis of it, it will give us Y, that is 7, and that is the value of T6. That is forecasted value what we are getting here. So this is a very simplified example of turning historical data and training a machine learning model and making a forecast from it. So there are some popular supervised ML models methods what we have, KNN, SVM, decision tree, random forest. So all these can be applied here to make such forecasts. So next question comes, what are the issues with this particular approach? And then the issue, the major problem what we have here is if there is a data has seasonality and it is and it has some stochastic trend and all, it is not going to be captured because we are only giving a limited time sequence or lag to it to learn. So it's not going to work in those complex situations. So let us see how we can model such situations. So next class of models to do forecasting is deep learning models, and here we have a multi-layer perceptron, that is a simple neural network that can be applied for this kind of modeling, and then a recurrent neural network. These are very efficient. It allows us to model a lag in data, and that helps us to mitigate a lot of drawbacks of time series modeling. And CNN, convolutional neural network, this usually applied into image classification or image processing kind of problems, but this can be also used into time series sequence problems. So let us look at one by one how all of these can be applied into time series forecasting. So let us look at multi-layer perceptron, and this is a typical representation, input output layer, and then these are hidden layers of MLP. And the advantage of these kind of models is robust to noise. So if data has a noise, it handles it pretty well. It could model nonlinear behavior very well. Also, if there are multiple inputs has to be given, so we know that multiple parameters impact this particular parameter which we want to forecast, then this will work well in those situations. And we can also do multi-step forecast. So it's not just next value, but we can forecast 10 next values or 15 next values. And of course, we have to give the fixed input and fixed output structure for this to work. So, and similar feature engineering, what we talked about with the ML models, has to be done here also to make these multi-layer perceptron models to work. So next is a CNN models we talked about, and this is being used particularly in image processing, so image or video processing. So what you see that in image processing or video, if you look at the video processing, we have frames of videos, right? And every frame is a picture, and that frame is going into time. So that is there's a time sequence also. And every image is not a single point, but it has all these spatial variations, pixels here. So CNN allows us to do modeling of both temporal, that is a time sequence, and a spatial, that is into dimensions, 2 dimensions, 3 dimensions. So those pixels what we are looking at here. So those kind of models, and this is quite effective. It could extract features automatically, and also it does not need lag information to learn. So some application of CNN, what we see, this smart band and activity band, they automatically detect what kind of sports you are playing. So they utilize these kind of CNN kind of models. So they take all this sensors data and also time sequence. So certain activity if you're doing, based on that classification works. The third category we talked about was recurrent neural network and long short-term memory networks. So these have advantage that you can model lag here. So you can provide lag into data, and that help us to learn much better representation of time series. So it is again robust to noise. It is nonlinear. Modeling can be done very efficiently. It could take multiple input parameter. Could do multi-step forecast as we have seen in previous one. And also stationarity is not a precondition here. So you can give non-stationary data and it will work with it. And it has native support for sequences, right? So we learned about that time series is a sequence data, and this particular method has native support for sequences. So it does that modeling pretty well. And of course, it can learn temporal dependence, so it can model seasonality and all other trends, etc., very well. Okay, so if you want to build a LSTM model, then how this will work? And this slide just gives a very high level architecture of it. So we get historical data. We try to get features which are going to be X and Y, and then we do build a model using LSTM. Once we have trained model, then we can provide live data after cleaning transformation, and then we can have this forecasted value. And again, once we forecast something, after some time that actual value also will be available to us. And once we have those values available, then it can be compared against. And if error margin is becoming more over time, then we can again go and retrain these models. So sometimes these models drift as process changes, and that's where you have to do the retraining of the models. So what are the drawbacks of deep learning models? One thing is that it needs large amount of historical data. So at least you need 6 months to 1 year of data to train these models. And of course, these are computationally expensive. So it will take a long time to train and score. And these are black box models. So it can't explain very well the causes why this particular kind of evolution happened, why this particular kind of forecast has come from these models. So that is not very easy to explain. And of course, if process drifts, then errors will increase, and then we have to retrain these models again. So we have covered the modeling part, both classical approach and ML approach. And very quickly, we look into some use cases into the industry. And first one is a CO2 slip forecast in ammonia manufacturing. So this is typical block ammonia manufacturing, where we take natural gas as feedstock, and it goes through a reforming process where natural gas is converted into hydrogen, which is being used as a raw material for ammonia manufacturing. But along with hydrogen, it also produces carbon dioxide and carbon monoxide. So, and that is poison for the ammonia synthesis, ammonia catalyst. So that must be removed in this particular process, CO2 removal and methanation process. And sometimes this does not work very well, and CO2 does not get removed. And if a significant amount of carbon dioxide goes out of this system, then it calls for a plant trip. So it is very important to understand when these kind of events are happening, when we are getting high amount of CO2 out of this process. And that's where we built a ML model here, and took around 20 parameters with a lag of 8 hours and forecast of 8 hours. It was trained on 6 months of historical data. And once we have trained model, then we started streaming with the live data. And here the result we see with the live data predictions. So actual, the red one is actual and blue one is a predicted ones. So it has picked up quite well all these excursion of CO2 what we are seeing before 8 hours of the actual event. Another, and this was a recurrent neural network LSTM kind of models, which is being used in this particular use case. Another use case is a glass furnace temperature forecast and optimization. And so this is a typical flow of glass manufacturing, where we take raw material and melt it into a furnace, and then finally it goes into molding and finishing process to have a final product. So the furnace temperature is very important, and it must be put into very tight range to have better energy efficiency and better product quality. So we applied similar models around 10 plus parameters. We give around 12-hour lag forecast, that is 12 hours in future, and we trained it over a year of data. And then once trained model was available, then very similar way we started streaming with live data. And these are some results what we see, that temperature forecast, which is and this is showing predicted actual versus predicted delta, which is quite close. So errors were very minimal here for both ground and bottom temperature. And once we know that what are the predicted values, what are forecasted value ahead of time, then we can put an AI optimizer on top of it, which could give us some further indication that what kind of set point has been put for this a particular furnace. For example, how much fuel you have to put, how much air you have to put, such that we can have a temperature in tight control range. So so now we came to end of today's presentation, and to summarize everything, what we see, that time series modeling is complex, and reason being this temporal structure, which make it a bit difficult. And conventional statistical time series analysis we can do, and you can understand data better. Explainability is much better in there. But it lacks modeling the complex non-linear data and also multivariate data. So their deep learning models comes handy, and it can do multi-step, multivariate, non-linear modeling very well, which we can apply. And we already have good number of live implementations into industrial domain of these kind of forecasting problems. So now over to you, Tyler, for the poll question.
All right, fantastic. A lot of information there, Sudhanshu. Thank you very much. We are going to finish up here. We got one final poll question just to see how much you guys got out of this. We're always trying to improve. We put on a lot of online virtual events, which I will show you how to sign up for our last class here in a minute. But go ahead and get those votes in. We just want a little feedback. And then you can ask Sudhanshu any questions you had directly. So start typing those in if you haven't gotten those in already. And all right, looks like the majority of you have voted. Appreciate that feedback. And I'm going to actually take back the screen here. And all right, so like I said, we just continued the second PDM summer school in our series of AI pertaining to artificial intelligence in industry. But we do have one more class left. So if you are looking to attend that, all you need to do is go to symphonyindustrial.ai, go over to resources and drop down to AI Summer School. If you click that there, you can scroll down, and here is the registration for the last session here. They kind of roll into the previous two, kind of a conclusion to our AI Summer School Machine Learning and Image Analysis. You're definitely going to want to go ahead and register there. Seats are limited, so go ahead and reserve that. We hope to see you in the next session. Hope you got a lot out of this one. That being said, let's take a look at the questions. All right, Sudhanshu, could you please let you know how to perform time series analysis of vibration FFT data? The goal is to predict anomalies in FFTs.
Yeah. So we can do some feature engineering on vibration data. So we can extract out some of the peaks, 1x, 2x, 3x kind of information from there, and we can weave it through a time series. So, for example, suppose we are